Hello everyone, welcome to this video titled Section 5.5 on alternating series. In this video, I'm going to be taking you through a preview version of a Newton Alta assignment for Section 5.5 on alternating series. Please understand that the questions I see in this video may not be exactly the same questions that you see when you work on the assignment yourself. But the objectives should be the same, and hopefully the problems are similar enough that watching me do them here will help you out in some way when you work on the assignment on your own. All right, so here it is, our Newton Alta assignment page. The upper left-hand corner, you've got the title of the section with, you will not see the word preview. Upper right-hand corner, you have the mastery bar that shows you how far along you've gotten, along with the activity log. It shows you all the objectives and how far you've gotten with each objective. Looks like there are 3 objectives for this assignment. And on the main page, you have a current objective, and beneath that, a question related to that current objective. And at the bottom of every question, you'll see a feedback button. This is for, if you see any typographical errors or any problems with the answers or answer explanations, you can send feedback directly to Newton, and hopefully someone will get back to you and fix the problem. You will not have this instructor cheat button, right? This is for instructors only. But you will have a more instruction button. All right, so if you're struggling with a topic or a particular question, try clicking on this and it'll take you to another page with some reading to do or videos to watch or both. And then you'll be given questions, related to that instruction. And you can work through the assignment this way. You can click on more instruction for every single problem if you wish. And there's absolutely nothing wrong with that. Okay. So our first question. We're talking about alternating series here. Now I'm in the objective here. The first one they're throwing at me is approximate the sum of an alternating series. All right, so first I want to, before I get into this example, talk about what an alternating series is, and then also go over the alternating series test. All right, one of the objectives is determine whether an alternating series converges. So I will talk about the alternating series test, which is sometimes referred to as the Leibniz test, but in this text, it's alternating series test. So before this example, let's go talk about alternating series. All right. Now, in all the sections before this, sections 5.1 through 5.4, especially 5.2, 5.3, and 5.4, you had the divergence test, remember, was just if all the terms of the series are not going to 0, then it's divergent. But then you had your integral test, and we used integrals to estimate sums, convergent sums. Then last section we had comparison and limit comparison tests. For all those tests, the integral test, the comparison test, the limit comparison tests, when we were estimating sums with integrals and stuff like that from the previous sections, for all those series, the terms of the series were non-negative. or there were a finite number of negative terms, and then eventually infinitely many non-negative terms. But all the terms were, non-negative and decreasing. Those. Here, when we're talking about alternating series, we're going to start looking at series that have infinitely many negative terms, along with infinitely many positive terms. So an alternating series looks like the following. We have the infinite series, sum from n equals, say 1 or 0, to infinity. And then for these alternating series, when we look at the terms that we're adding up, there's going to be this power of -1. I'll write -1 to the n plus 1 power here. It could just be -1 to the nth, but you'll see this power of -1 show up, multiplied by, and then some rule for another sequence. Say they're using b sub n in this text here, where all the b sub n's are non-negative. All right. So these b numbers are not negative. What will make them negative is when I multiply by -1, some power, some odd power of -1. But you see something that looks like this. When n equals 1, you got -1 squared, so it'll just be b1, right? Positive b1, a positive number. So there's one positive term. And then when n equals 2, we'd have -1 to the third, which is -1 to an odd power, which will be -1. So the next term will be minus and then b2. b2. So positive term, negative term, right? Again, since b2 is positive, right? b2 is positive, minus b2 will be negative. And then we'd have plus b3, minus b4, plus b5, and so on. This is called an alternating series, where it's positive term, negative term, positive term, negative term, or negative, positive, negative, positive. As long as it's alternating, switching back and forth between being, having a sum, having a positive term and then having a negative term next in your sum. So now, along with this, we'll talk about the alternating series test. When will such a series converge? Right? When will it actually, adding up more and more terms, when will it converge to some, finite value? And it's a very simple test. Alternating series test. So suppose we're given an alternating series. Sum from n equals 1 to infinity of this whole -1 to the n plus 1 power, -1 to the nth power, some power of -1 times the terms of a sequence of positive numbers, right? Again, b sub n, and same definition up here. So with, b sub n, all the b's are non-negative, all right? And this whole power of -1 causes the alternating terms, positive, negative, positive, negative. So suppose we're given an alternating series. If, if it's alternating, cool. If the B sequence, right, the sequence of B sub n's is a decreasing sequence, all right, remember what that means. That means B sub, n plus 1 is smaller than B sub n. You could say less than or equal to as well. Might as well throw that there. But but every term is, no bigger than the term before it. It's getting lower and lower. And, of course, remember our divergence test from section 5.2. The terms of this B and C, the terms that we're adding up, remember they have to approach zero if if a series has any chance of being convergent. So if if these terms that are alternating, these B's are decreasing, getting smaller and smaller, and approaching zero, right, the limit as n approaches infinity of the B's is equal to zero, then our series will converge. So very, very small amount of things to check here. Then the alternating series will converge. Oops, that's a G, sorry, will converge. Now, if this stuff isn't happening, now suppose the terms go to zero, but it's not necessarily a decreasing sequence. Maybe it's going up and down and up and down and up and down towards zero like that. Then we can't really say anything with this. Okay, it's got to be for a decreasing non-negative sequence Bn that's approaching zero. That's got to be the condition that's met in order for such an alternating series, in order for us to say it converges, and be correct. Now, if B sub n's not decreasing, it could still be convergent. It's just we can't really say anything with this test. All right, so just be careful. And then, of course, if the terms aren't going to zero, divergence test, tells us that it's divergent. Right? All right, and then finally, to the objective at hand, right? So now we know what it, again, we know what it, we'll see examples throughout the assignment. So I'm not writing examples up here just yet, but we see what an alternating series looks like, should look like. We know some condition for when we can say for certain when an alternating series will converge. And then if it's convergent, right, what will it converge to? Can we approximate the sum of an alternating series? So now that comes to this, approximating the sum of an alternating series. And of course, this is only going to be for convergent alternating series, right? If it's divergent, there's no need to approximate anything. It's not actually, the sum isn't approaching some finite value. So suppose we have a convergent alternating series, right? So the sum from n equals, again, 1 to infinity of some power of -1, which will cause the alternating again, I'll write -1 to the n plus 1. It could be -1 to some other power, but times, and then your sequence of non-negative terms that are also decreasing and going to zero, right? So suppose I have an alternating series that is convergent. Again, B sub n decreasing. Let's just suppose it satisfies those conditions from the alternating series test. B sub n decreasing, B sub n, approaching zero. Okay, all these things. Well, let's say it's convergent to, capital S, right? S. So I'm going to show you a little thing here on a number line. So here's a number line, real numbers. Right, and what we're told is that the series converges to, S. Let's say zeros over here. Okay, so let's just say S is a positive number. It doesn't have to be, but let's just say S is positive for the picture. Now, the first term that would be added, so I start off at 0, of course, and then the first term that would be added would be B1. Right? So let's say B1 is positive, right? So B1. So I go from 0, I add B1. And then we'll subtract B2. And B2 needs to be smaller than B1. Remember I said that we're assuming this alternating series satisfies the conditions of the alternating series test. We'll have to check that when we do these approximations, but so from B1, I will then subtract B2, which will take me, say, over here. Now, instead of writing B1 minus B2, I'm going to call that S sub 2. Remember that, and this is notation from before, S sub capital N was the sum, the nth partial sum, right? The sum of the first capital N terms of the series. So B1 is just S1, and then I subtract B2. So again, B2 needs to be less. So I go from here, I minus B2, and it needs to be smaller than the B1. And then I'll add B3, which will take me over above S, right? And you'll see this with these convergent. So here's S3. So again, and B3 should be shorter than B2, right? So there's plus B3. And so on. So eventually, right, so we'd subtract B4, add B5, right? Here's S4, S5, S6, S7, and so on. Eventually, we'd get down to, say, S sub capital N, right? And then something else to remember is R sub N. Remember, this is the error. This is the error, slash remainder after adding the first n terms. And we could call this, the absolute value of S minus S sub N. This is how far off is the partial sum, the nth partial sum from the actual sum itself, right? What the series converges to. So that's this distance here. Say this is capital S sub n. This distance here is, going to be R sub n, or the absolute value of R sub n, right? And if you've been noticing this error, see how R1 was smaller than B2, and here's S3, or sorry, S2. R2 would be the distance from S2 to S, and that was smaller than B3. And then from S3 to S, that would be smaller than B4. This would be smaller than B sub n plus 1, because I would go from Sn, say, and then subtract b sub n plus 1. And that'll be smaller than, the previous term. Yeah, you see that R1 smaller than B2, R2 smaller than B3, R3 would be smaller than B4, and so on. Rn is smaller than just B sub n plus 1, the absolute value of the next term that's being added on. So yeah, very simple condition here. So the absolute value of our error is less. So the sum of so when I add up the first capital N terms, how far off we are from the actual sum is less than just the next term that we would add on to b sub n plus 1. Right, so this is we're going to apply here to get certain levels of accuracy. Right, and let's actually now apply this to the example we were given, right? So finally getting to the example here, 20 minutes in, but that I've explained all the stuff that's going to apply to these first two objectives about alternating series. So we're asked to estimate the value of the convergent series. So you see they tell us this is convergent by adding up the minimum amount of terms to ensure an absolute error less than 0.001. Round your answer to 6 decimal places if necessary. So we'll do this here. All right, so here's the sum. So for example, right, the sum they give us from n equals 1 to infinity of 11 times, and then see this power of -1 showing up here, -1 to the nth, that'll cause the alternating, divided by, and then 3n plus 1 factorial. This exclamation point, I'm sure we've seen this in a previous video, but I'll explain it again here real quick. Factorial just means you're multiplying from 1 up to that number. So like 1 time, so like for example, so again, this is factorial notation, the exclamation point. 5 factorial is 1 times 2 times 3 times 4 times 5, which would be 120. And 4 factorial would be 1 times 2 times 3 times 4, or 4 times 3 times 2 times 1. You can start at that number and go down to 1. You're just taking a big product, and this would be 24, and 3 factorial would be 3 times 2 times 1, or 1 times 2 times 3, that would be 6, and 2 factorial, 2 times 1 is 2, and 1 factorial would just be 1. And then something that is defined so things don't get messy on us is, and again, if you followed the pattern here, 0 factorial. Well, when I start with 5 factorial, to get to 4 factorial, I divided by 5, and then I divided by 4, then I divided by 3, then I divided by 2. So now I divide by 1, to get to 0 factorial. So it's still 1, right? So keep that in mind if you ever see 0 factorial, that is 1. Anyway, so that's factorials real quickly. So let me write out, I'll show you the first several terms of this, and we'll see that it's alternating. When n equals 1, this will be negative, 11 over, and then 4 factorial, which would be, 24, negative 11 24ths. And then when n equals 2, we'll have -1 squared. This will be positive, 11 over, and then 7 factorial, which would be, 7 times 6 times 5 times 4 times 3 times 2 times 1, which is definitely bigger than 4 factorial. Minus 11 over 10 factorial, which is bigger than 7 factorial, and so on. So it's definitely alternating because of this whole power of -1 thing. And the b sub n here, what terms are alternating is, the stuff that's not attached, the stuff that's attached to the power of -1, this here. That's your b sub n that I was talking about before. It's this 11 over 3n plus 1 factorial, which is definitely non-negative. Right? It's non-negative, definitely approaching 0, right? Because the denominator will be getting very, very large, right? 4 factorial, 7 factorial, 10 factorial, 13 factorial, blah, blah, blah. Getting much, much larger than the numerator, which is just 11. So it's definitely approaching 0 and decreasing, right? The higher, every term is much smaller than the term before it, right? 11 over 4 factorial is bigger than 11 over 7 factorial, and it's bigger than 11 over 10 factorial, and so on. So by the alternating series test, the series converges. Now, I know they told us this already, right? But I would say series converges, by alternating series test, which will apply to other series later as well. Right? All right, so now I know they told us that it converges, but I just wanted to show you, what we would be applying to other series. Okay, so the series converges. Now they're asking us to estimate the value of this series so that the absolute error, again, this would be that absolute value of that r sub n that I was talking about on the top of the page here, right, the last page, is less than 1,000th, right, 0.001. So we need to satisfy this inequality here. Well, from what we saw before, with these convergent alternating series, right, the absolute value of r sub n, right, the absolute value after adding up the first capital N terms of the error after the first capital N terms will be less than just the n plus first term that's added on without, again, plus or without the minus. Right? If it's a minus, don't worry about it, right? We're just keeping this as absolute value of the error. Well, what does that look like? B sub, capital N plus 1 is this 11 over 3n plus little n plus 1, where I replace little n plus 1 with capital N plus 1. Right? So this would be 11 over, and then 3 times, replace little n with capital N plus 1 here, and then plus 1, factorial. And then the question is, when is this less than 1,000th? Right, when is this less than 1,000th? Now, if you do some little manipulation here, now this is 3n plus 3n plus 3 plus 1, so this is 3n plus 4 factorial. I'm going to multiply that over here and then multiply by 1,000, right? So I multiply by this, get 3n plus 4 factorial in the numerator there, and then multiply by 1,000. When is this greater than 11,000? Sorry, this should be capital N, right? So 3 capital N plus 4 factorial. When is that greater than 11,000? All right, so I went through some factorials earlier, right? 5 factorial is 120. 6 factorial is 6 times 5 factorial, so that'd be 720, right? 6 times 120, not bigger than 11,000. So I'm just looking for what factorial would be greater than 11,000, right? 7 factorial, that's 7 times 6 factorial, right? It's just the previous thing times 7, which would be 5040, not bigger than 11,000. And then finally here, 8 factorial, right? That's just 8 times the previous one, 8 times 7 factorial. That's bigger than 11,000, right? That'd be 40,000, right? And then plus 320, right? That's definitely bigger than 11,000, which is what I'm looking for here. So when this number is 8, that's when we satisfy the inequality. So when 3 capital N plus 4 is, greater than or equal to 8, that's when this is satisfied, right? Because obviously if 8 factorial is greater than 11,000, so is 9 factorial, 10 factorial, and so on. And then solving for capital N here, subtract 4, divide by 3. N has to be greater than or equal to 4/3. So, because N has to be an integer, right, and capital N is a number of terms we're adding up, N has to be greater than or equal to 2, right? This is 1.3 repeating. So what this is telling me is that the remainder after adding just 2 terms is less than what they want. So this is saying S sub 2 will be accurate, will be at the desired level of accuracy. All right, so all I need to do is add up the first 2 terms, right, which I have up here. Right. Here's S sub 2. Right. Now they said round this to 6 decimal places, so I'm going to go to a calculator and just punch those in. Right. So I'll actually write up the sum. No, I'll just put in the numbers that we had. Negative 11 over 24, right? 4 factorial. Plus 11 over, and then 7 factorial. So this is negative 0.456151 when I'm rounding to 6. The sum of the first 2 terms. Now let me show you. I'll actually put the sum in. We'll go from 1, n equals 1 to x of 11 times negative 1 to the n divided by, and then 3n plus 1 factorial. And make a little table here. And yeah, you see the sum of the first 2 terms. This is what we got up here, right? Negative 0.456150079, blah, blah, blah. Now look, when I add up more and more terms, 10 terms, 100 terms, 1,000 terms, after a while it stops changing here. So this is at least the first 6, because again, the 7th one might be rounded. So, oh, sorry, the 8th one might be rounded. So this is the first 7 decimal places of accuracy for what this series is going to converge to. It'll converge to negative 0.4561538 something. Well, you see, after adding the first 2 terms, we're definitely within 1,000th, right? If I were to subtract these values, the error is no, look at they're definitely within 0.001 of each other. In fact, are some of the first 2 terms is actually accurate to the first 5 decimal places, 0.45615. So the error is definitely less than 1,000th, right? If I were to subtract these values, it'd be less than 1,000th. But they want us to just do the minimal amount, right? I would only need to add up the first 2 terms, and rounding that to 6 decimal places, get negative 0.456151. So back here, this sum is approximately negative 0.456151 when rounding to 6 decimal places. Great. Again, they'll run you through the error thing. Right, the absolute value of our error after adding n terms should be less than or equal. No, I said less than the next term we add on, the absolute value of the next term that gets added on. And yeah, that's going to happen from 2 onward, right? So S2 was all we needed to get an approximation within the desired level of accuracy. Oh, and of course, after you answer any question, whether you get it right or wrong, they give you some sort of answer explanation. Please read through these. Now, if you're correct, maybe they'll do something in a way you like better that you might want to do in the future. If you're incorrect, definitely read through them to make sure you can see, hopefully you can figure out why you were wrong and then fix that in later problems. Okay, moving on. All right, so we're asked to do the same kind of thing here. Determine the number of terms. Now this is just how many terms would be necessary. So in the last example, that would have been 2 terms, right? The sum of the first 2 terms from the last example gave me the desired level of accuracy. So we're asked to determine the number of terms necessary to approximate the sum of this following series. So this is another convergent alternating series with an error of less than, again, 1,000th. So here's another convergent alternating series. We have the sum from n equals 1 to infinity of 9 times -1 to the nth. Right, here's this power alternating. That'll cause the alternating, right? This power of -1 divided by 4n plus 1 factorial, right? So this would look like this. You'd have negative 9 over 5 factorial. So that's -9 over 120 plus, and then 9 over 9 factorial minus 9 over 13 factorial plus 9 over 17 factorial, and so on, right? Alternating negative, positive, negative, positive. The b sub n here, right? The terms that are being alternated are these 9 over, right? 9 over the 4n plus 1 factorials, which are definitely non-negative, right? These are all positive numbers. Definitely going to 0, right? The denominator will be getting huge as n goes to infinity, and definitely decreasing, right? Because every single term gets smaller and smaller. Forget if you ignore the negatives, right? Every term gets smaller and smaller and smaller. Every term is smaller than the previous one. So all these tell me that this is a convergent alternating series, right? By that alternating series test. Now I know they said it's convergent already, right? They're giving us a convergent sum, but I just want to apply the alternating series test again. Talk about the conditions that need to be met. Okay, so remember we're looking for this, what's capital N? How many terms do I need to add so that the error, the absolute error, is less than 1,000th? Now, remember I said this earlier, now I could do less than or equal to as well, but we got this going on. For alternating series, right? For these convergent alternating series, absolute error, after you add the first capital N terms, is smaller than just the n plus first term of the sum without a minus, right? Take the absolute value. All right, so this would be 9 over, and then 4 times, I'm replacing little n here with capital N plus 1, and then plus 1, factorial down here. And we want this to be less than 1,000th. Again, they want it to be less than 0.001. All right, so I'll do the same thing with this inequality. Multiply. You got 9,000 on the left now. Would be less. This will be 4n plus 5. I'm going to just put the 4 here. This is 4 times capital N plus 5 factorial. And we saw a lot of factorials in the last example. I want to know what factorial would be greater than 9,000, and that's going to be 8 again, right? 7 factorial is not bigger than 9,000. 8 factorial is. So again, this this 4n plus 5 must be 8 or greater. All right, 8 factorial or greater would be greater than 9,000. And then solving this for capital N, we'd have n must be greater than or equal to, 3/4. But because n needs to be some integer, some whole number, I'll say n has to be greater than or equal to 1, something bigger than 3/4. So 1 or greater. If I add one term of this series, I'll get the desired level of accuracy. So S sub 1 will give the desired level of accuracy. Now they don't need what S sub 1 is. All they were asking for is what was that capital N. How many terms would need to be added to get our estimate to be within 1,000th of the actual sum? At least one term is needed. All right, the first term of the sum would give us the desired level of accuracy. Again, they run you through the explanation here. Great. All right, moving on. All right, so now we're just asked to determine whether an alternating series converges. That's the title of the objective. All right, for what values of p is the series below convergent? All right, so I'll write this out. Go over those conditions of the alternating series test again and see what values of p would make those conditions be satisfied. All right, so the sum is this, right? Sum from n equals 1 to infinity. And then the terms we're adding up are 2 n to the p times -1 to the n minus 1 power divided by 6. Which I can clearly simplify to, let's do that. This will be n to the p over 3, right? 2 over 6 times and then -1 to the n minus 1. All right, so this is definitely alternating, right? You'd have, when n equals 1, -1 to the 0, that'd be just n to the p over 3, or sorry, 1 to the p over 3, n equals 1. So 1 to the p over 3, and when n equals 2, this will be -1 to the first, which would be -1, and then, it's a minus, and then 2 to the p over 3, and plus 3 to the p over 3, minus 4 to the p over 3, and so on. Right? So the b sub n's here. That's the b sub n's. Right? This n to the p over 3. Now, maybe looking at some of these terms here, 1 to the p, 2 to the p. If p is positive, if you just had n over 3 or n squared over 3 or whatever, n to the half over 3, square root of n over 3, whatever. If p is positive, these would be going to infinity as n goes to infinity, right? The series would diverge, right? Series diverges in that case because the terms of the sum, right, all these terms that you're adding up wouldn't be going to 0. All right, so p can't be greater than 0. And actually, it can't be equal to 0 either, right? Because if p were equal to 0, you'd have n to the 0, that'd just be b sub n here would just be 1/3 all the time. right? So you'd have 1/3 minus 1/3 plus 1/3 minus 1/3. The terms are not going to 0. They're going to 1/3. So again, we'd say the series would divergent. It's only when p is less than 0, right? So like, say, for example, I had n to the -1 over 3. Well, that would just be 1 over 3n, right? And n to the -2 over 3, that'd be 1 over 3n squared, right? These are positive terms. They're going to 0, and they'd be decreasing. Right. They satisfy all the conditions, these 1 over 3n, 1 over 3n squared, whatever. But when p is negative, that's when the series will converge by the alternating series test. Remember those conditions for an alternating series, the terms that we were alternating where, you're alternating some non-negative stuff. They go to 0, which all these would when p is less than 0, and they're decreasing, right? So every term would be smaller than the previous one. And that's happening with these, 1 over 3n, 1 over 3n squared, 1 over 3n cubed, whatever. So yeah, the value of p would have to be negative in order for us to, the terms of our series to satisfy the alternating series test conditions. So p has to be less than 0 here. Great. Again, they read through the answer explanations, please. All right. So now it's the third objective. Understand absolute convergence and conditional convergence. Okay. So let's talk about those definitions. What do those mean? All right. So say we're given, some infinite series, some from, and start. I'll just have it start at n equals 1 again. 1 to infinity of a sub n. Now, this could be any series, all right? It could be a series of all positive terms, all negative terms, but if it was all negative terms, I would just factor out the minus and look at the series of all positive terms. Or it could be a series with, finitely many negative terms or infinitely many negative terms like our alternating series. This could be any series, any infinite series. If I were to make all the terms positive or non-negative, so take the absolute value of every single term. So this is, make all the terms of our series non-negative. If I make all the terms non-negative and the series of non-negative terms converges, then we say that the series is absolutely convergent. Then we say that the series that we were given initially is absolutely, oops, can't spell, ABS, right? Absolutely convergent. Now, if I make all the terms non-negative, if I take the absolute value of every term and this series diverges, then it's not absolutely convergent. All right. Now, here's a very, very nice result, which you can read the proof for in your textbooks or in the sure we got the proof for it in the more instruction here. The video is already getting long enough. But here's a nice, very, very, very important result. I'll put 3 stars here. If a series were given is absolutely convergent, so if a series is absolutely convergent, meaning I make all the terms non-negative and that series converges, the series of non-negative terms converges, then the series will converge. The original series, I'll say the original series. All right, the one we were given will converge also. So remember what it means for apps to be absolutely convergent is if I make all the terms non-negative and that converges, right? If I make all the terms of a series non-negative and that converges, then the original series would also converge too. Now, they're not going to necessarily converge to the same thing, right? So I want to do an example here. Right. Say we're given this sum from n equals 1 to infinity of, and I'll make it alternating. I know we could say it's convergent by the alternating series test, but let's go -1 to the nth over n squared, right? So here's my a sub n. If I look at make all these, non-negative, right? So this sum here would be -1 plus 1 over 4 minus 1 over 9 plus 1 over 16 and so on. I want to make them all positive. So instead of, that'll get rid of this -1 here, just do the absolute value. Right? Make it all positive. This is the absolute value of all these a sub n's. This sum would be 1 plus a quarter plus a ninth plus, 1/16. It's just all the terms of my original sum made positive. Well, we know from earlier sections that this is convergent. This sum of the positive terms, right? This is a convergent P series. Right? 1 over n to the P, where P is bigger than 1. And since this sum of positive terms is convergent, right? So since this converges, we would say that the original sum is absolutely convergent. And what I was saying here by the 3 stars, if a sum is absolutely convergent, then it is convergent, right? So because something's absolute, when you say that a certain sum is absolutely convergent, then you can say the sum itself will converge. Right? That's a very, very nice result. Is convergent. Right. Now that again, that doesn't mean they converge to the same thing. This sum up here converges to pi squared over 6. That's a famous result. If you were to add on more and more of these terms, it'll get closer and closer to the value pi squared over 6. This sum here does not converge to pi squared over 6. Okay, they'll converge to different stuff. Because this has no negative terms. This is a bunch, infinitely many negative terms. But it will still converge. And we can use again, this is also a convergent alternating series. You can do the alternating series test for this. And because it's alternating and convergent, we could do that remainder thing that we saw, do a nice estimate to within a certain level of accuracy that we saw earlier in the video. Right. Now, I'll also give you an example of a series that's not absolutely convergent. So say just the alternating harmonic series. So this would be -1, plus a half, minus a third, plus a fourth, minus a fifth, and so on. So here's the sum of our, a sub n's. Do the absolute, right? To take the absolute value of every term, make every term positive, that'll just be 1 over n, plus a half, plus a third, plus a fourth. That just takes all the terms from my previous series and makes it non-negative, right? So this is the absolute value of a sub n that I'm adding up. And we know that this is divergent, right? This is that harmonic series, right? So when I make all the terms non-negative, it diverges, meaning that the original sum we were given, right, that sum from n equals 1 to infinity of -1 to the nth over n, is not absolutely convergent. It's not absolutely convergent. However, it is convergent. The sum from n equals 1 to infinity of -1 to the nth over n is a convergent alternating series. You could apply the alternating series test to it, right? Because it's alternating, sure, right? You got negative, positive, negative, positive, negative, positive. All the terms that are alternating, 1, 1/2, 1/3, 1/4, those are positive numbers that are decreasing to 0, right? Decreasing and decreasing to 0. So it passes the alternating series test. So I have a series here that's not absolutely convergent, right? So if I make all the terms positive, it diverges. But on its own, it's convergent, right? If I look at just the original series itself, it converges. Um, so a series like this, so another definition, a series like this would be called conditionally convergent. So if I have a series that is convergent, but not absolutely convergent, so I have a series that's convergent, not absolutely convergent, right? If I made all the terms positive, it would diverge. Then we say that the series we were given is conditionally convergent. Right? So it's only convergent as is under that condition. Yeah. It's not absolutely convergent. If I were to make all the terms positive, it diverges. And yeah, we just saw this sum here, right? This alternating harmonic series, the -1 to the n over n sum. This is a conditionally convergent series because it converges on its own But when I make all the terms positive, it diverges. When I look at trying to see if it's absolutely convergent, it diverges. And something we'll probably not talk about, I don't think it's in these problems here, but we'll see. But we'll see later, if a series is conditionally convergent, you can actually rearrange the terms of that series to have it be convergent to any value you wish. All right, because there'll be infinitely many positive numbers, infinitely many negative numbers. So you just rearrange the terms so that you add on enough positive numbers to be greater than your sum, then you add on negative terms to be less, and then greater than less, then greater than, until you hone in on the sum that you want. Again, I don't think that's going to come up here, but we'll see. All right, so finally back to this example. I know a lot of explanation in this video. There's a lot of definitions and stuff and nice results. So we're given this series, right? Pardon me. So we're given this alternating series, and they're asking us if it's convergent absolutely or conditionally. Because they're telling us, look, they're telling us it converges. All right. So the terms that you're adding up here are decreasing to 0 and positive, right? And then they're alternating. But the terms that you're adding up, this n plus 1 factorial over n plus 2 factorial, those terms are going to be decreasing to 0. And it's alternating. So it passes the alternating series test. This would be convergent. Question is, does it converge absolutely? So if I were to make all the terms positive, get rid of this -1 to the n plus 1 power, basically, would that series converge? All right. So we have the sum from n equals 1 to infinity of, -1 to the n plus 1 power times, and then n plus 1 factorial divided by n plus 2 factorial. Now, remember factorials I've been talking about. N plus 2 factorial, that would be n plus 2 times, and then n plus 1 down to 1, n plus 1 factorial. So you'd see the n plus 1 factorials canceling. I'd be left with n plus 2 in the denominator. So this is the same thing as the sum from n equals 1 to infinity of just -1 to the n plus 1 over, and then just n plus 2. All right. So this would be 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6, and so on. Now they're telling us this is convergent. Right? It's a convergent alternating series. It passes all the tests. The 1 over 3, 1 over 4, 1 over 5, 1 over 6, those are going to 0 and decreasing. And it's alternating. So it's a convergent alternating series. Let's do the absolute value of everything. All right, let's see, is it absolutely convergent? So that's this sum. Sum from n equals 1 to infinity of basically just get rid of the minuses. That should just be 1 over n plus 2, which would be, 1/3 plus 1/4 plus 1/5 plus 1/6. Remember, we could do a easy limit comparison. Say this is, if I do a limit comparison with just 1 over n, right? You see how all these are like 1 over n basically? And you do 1 over n plus 2 divided by 1 over n and see what happens as n goes to infinity. Well, this would just be 1, this limit, because you would flip and there would be n over n plus 2, and that's approaching 1, remember, which is not 0, okay, and it's not infinity. So remember, the limit comparison test tells us that the sum then from n equals 1 to infinity of 1 over n and 1 over n plus 2 that I compared to will both converge or diverge, and we know this is divergent. Right, so this must also be divergent. Okay, so what we have here, the original sum we were given, this alternating sum, converges. But when I make everything positive, take the absolute value of everything, it diverges. So this is one of them conditionally convergent series. All right, conditionally convergent. All right, the original series converges the way it is, but when I make everything positive, it diverges. Right? That's called conditionally convergent series. So the series converges conditionally. Now, if I made all the terms positive and it converged, we say it converges absolutely. Right. And then, of course, if the original series just diverges, you know, we'll still make everything positive to see if it converges absolutely. But if the original series diverged, though, it wouldn't be absolutely convergent because remember I said earlier, if something's absolutely convergent, then the original series is convergent, right? So the contrapositive of that is if the original series is divergent, then it's not going to be absolutely convergent. It'll be absolutely divergent, right? Okay, submit convergence conditionally, cool. All right. And they give you the definitions here again. All right. And did they do a limit Yeah, they did limit comparison, just like I did. Cool. All right, so same thing. Determine if the series below converges absolutely, converges conditionally, or just diverges. So again, I'll write this up. So we're given an alternating series, right? We have the sum n equals 1 to infinity of this, again, you got this power of -1 showing up here, giving it away that it's alternating over 6n plus 5. So this would be, 1 over 11 minus 1 over 17 plus 1 over 23 minus 1 over 29 and so on. Alternating series. The terms of the sum, that you're alternating this is 1 over 6n plus 5. These are definitely non-negative. They're definitely approaching 0 and definitely decreasing. Okay, I mean, you could do more thorough checking of that, but as I go further along, right, the denominator just keeps getting bigger and bigger, which will make each term get smaller and smaller. So it's decreasing to 0. So this is a convergent series, right? Convergent by the alternating series test. Right, so this converges the way it looks. Let's make everything positive. Right, so I'm going to go down here. And again, when you make everything positive or take the absolute value of every term, that's just going to get rid of this power of -1, especially for these alternating series, right? So this will be just 1 over 6n plus 5, which would just be 1/11th plus 1/17th plus 1/23rd plus 1/29th, right? Again, it's the same as the original series, but all the minuses become pluses, right? I'm going to do a limit comparison again with 1 over n. 1 over 6n plus 5. That's very much like 1 over 6n, which is close to 1 over n. It's a multiple of 1 over n. Take the limit as n approaches infinity. And I hope you can see that this would just be 1/6, which is not 0 and it's not infinity. And remember, if that's the case, then both series converge or diverge. Well, we know that this series of the 1 over n's diverges, right? Divergent p series. So this must diverge as well. Okay, so what happened was, the original series converges, convergent alternating series. When I make everything positive, it diverges. So it's not absolutely convergent, right? Not absolutely convergent, but it was convergent initially. So we call that again conditionally convergent, right? So this series we were given is conditionally convergent, right? So the series converges conditionally. Right. Now they did a direct comparison, whatever. Right. Oh no, they did a limit comparison as well. So now we're given an alternating series, asked to determine whether it converges or not. Right. So determine if the series below converges or diverges using the alternating series test. If the alternating series test does not apply, use the nth term divergence test, right? Do the terms even go to zero, right? That was the divergence test. All right. So let's see if I can figure out a little rule here for these terms. We got -1/9 plus 1/5, right? It's alternating, so it's going to go negative, positive, -3/11 plus 1/3 -5/13 and so on. Okay, so definitely alternating. Oh, okay, I see what this is. This is 2/10. This is 4/12, 1/3. Yeah, so what we have here is this sum. We go from 1 to infinity, -1 to the nth because it's starting off negative. And then every single one of these has, the numerator is just whatever n is, right? So times n. The denominator is starting at 9, and this, 1 keeps getting added. So down here, n plus 8. All right, it's got to be n plus 8 because it's just both the numerator terms, the 1, 2, 3, 4, and the denominator terms 9, 10, 11 are arithmetic sequences. You just keep adding 1 every time. Yeah, so this sequence here isn't even approaching 0, right? N over n plus 8 is approaching 1 as n goes to infinity, so it doesn't satisfy the alternating series test. Now the terms may be decreasing, sure, but not right away. Because 1/9 is 0.111, 1/5 is 0.2. That actually gets higher. Yeah, so they're not even decreasing, you know. So they're not decreasing, they're not going to 0, not satisfying the alternating series test, but still this is not even 0. So the series diverges by that divergence test. And that was back in section 5.2. The divergence test was simply if the terms that you're adding up aren't even going to 0, then it's divergent. There's nothing else to do. So the series diverges. Yeah, okay. All right, so same kind, so this is absolutely convergent, conditionally convergent, or divergent again. All right, I'm just seeing right here. You see how, yeah, just like the last example. See how the power on n in the numerator was 1, the highest power on n in the denominator was 1. That didn't approach 0 then, right? The terms that you're adding up don't even approach 0. Same thing's happening here. Got n to the 6/5 up here, n to the 6/5 down here. Those are the highest powers of n in each of these. So as n goes to infinity, the terms are going to be, well, without the -1 to the n, the terms will approach 1, not 0. So this is divergent straight up. Right? The terms of this are going to approach 1 and then alternate back and forth between something close to 1 and something close to -1, but not approaching 0 at all. So yeah, series diverges. Very quick and easy, that one. And they explain that down here, I am sure. Right, see, the limit isn't even 0. Right? Okay, which of the following statements applies to the convergent alternating series? All right, so they're telling us this converges. We could easily see that though with our alternating series test as well, right? We're given this sum, n equals 1 to infinity. Now they have a minus sign here and then another -1 to the n plus 1 up here. This is like having another -1, this minus sign out front, and then 5 n to the 4/5 down here. So really I could put that -1 with the other -1. Now we could write this way. This would be -1 to the n plus 2 power. Oh, up here, and then over 5 n to the 4/5, right? So we'd have, when n equals 1, this would be negative 1 over, you know, 5 times 1 to the 4/5, and then plus 1 over 5 times 2 to the 4/5, and then so on, right? Now, the terms that we're alternating, that's 1 over 5 n to the 4/5, right? This would definitely be going to 0 as n got bigger, right? And decreasing, because again, the power, the number up, the number down here in the denominator would get larger and larger every single term. So every term would be smaller than the previous one. And they're all positive as well, right? Starting with n equals 1, these are positive as well, right? So greater than 0, approaching 0, decreasing. So yeah, I know they told us this, but this is convergent, this series, right? By the alternating series test. But now let's see if it converges, absolutely. So I just make all the stuff positive. So that gets rid of all these negatives here. We're looking at this sum. Right, just 1 over 5 plus 1 over 5 times 2 to the 4/5, and then plus, instead, it's just all the terms from the previous series, but, positive terms. Now I could do limit comparison, but you see how this is like the sum from 1 over, just 1 over n to the 4/5, right? So I would do a limit comparison with that. And this is a divergent p-series, right? Because you have 1 over n to the p, and p is less than or equal to 1/4, So this must be divergent as well. And you could do a nice easy limit comparison. So once again, we're seeing a series that is convergent, but not absolutely convergent, right? So again, they would call this series that I was given initially conditionally convergent. So series converges conditionally. All right, great. Yeah, so they're not having us do what I was saying earlier. I mentioned if a series converges conditionally, um, then you could rearrange the terms of that series to have it converge to any value you want. But we're not talking about that here, unfortunately. Okay, next question. All right, so back to, does an alternating series converge? Again, we're going to try to apply the alternating series test. And this is another one where they have values of p. For what values of p is the series below divergent? Right. So write this out. Now the only options are positive p or negative p. All right, so let's look at both of those. So the sum from n equals 1 to infinity. And you got this power on -1 here, making that would cause the alternating. And then your denominator is the natural log of 3n plus 2 to the p power. Right. So definitely alternating. So now look at the terms that are alternating. Just 1 over natural log of 3n plus 2 to the p. Now, if p were positive, for example, 1 over natural log of 3n plus 2, or 1 over natural log of 3n plus 2, squared, whatever. Starting at 1, you'd have natural log of something bigger than 1 down here. They'd be positive values, all these, and they'd be decreasing to 0. No matter what p is, as long as p is positive, you'd have a sequence of terms that were decreasing to 0. So when p is greater than 0, this series would be convergent by the alternating series test. When p is negative, right, when p is less than 0, you'd have, 1 over, say, natural log of 3n plus 2. I'll just look at this to the negative 1. That would just be the natural log of 3n plus 2, which definitely approaches infinity, not 0. And it's definitely not decreasing as n goes to infinity, right? So divergent, the series would be divergent if p was less than 0. And that's what they asked for, though, right? They asked for what values of p would cause the series to be divergent when p is negative. So read carefully. All right, so determine if the series below converges or diverges using the alternating series test. Again, all right, I'm just going to say this one out loud. The numerator has n. Denominator has, square root of 6n squared is the highest power term, which would be the square root of 6 times n. The terms that are alternating here would approach 1 over the square root of 6, not 0. So this is a divergent series. Right? That's really a simple test. Let's see, that I show you here. The approaches something that's not 0. Right? Okay, and then back to the initial objective we saw, where we're approximating the sum of an alternating series. So find a bound for the error when approximating the following series. Okay. By the partial sum S6. So this is going back to that, this is earlier on in the video. I talked about this in the very first example from this video. So let's write this sum up. All right, so we got the sum from n equals 1 to infinity of, and then 2 over n plus 1 factorial. And then you have times your, thing that'll cause it to alternate, this negative 1 to the n plus 1. So remember this, so this is called the b sub n, right? That from the alternating series definition, right? It's 2 over n plus 1 factorial. These are the terms that are alternating in your sum. And recall from earlier, your error, right? The absolute error will be less, or less than or equal to, but I'll just say less than, b sub n, capital N plus 1. And after adding the first capital N terms, the error will be less than just the next term that you're adding, or the absolute value of the next term that you're adding. So they're saying when I add up the first 6 terms, what's the error going to be less than? How accurate is the sum of the first 6 terms of this series going to be? So this should be less than or equal. Again, this is less than or equal to b sub n plus 1. So I'm just taking this here, replacing little n with capital N plus 1. So that'll be capital N plus 2 factorial, right? Because you have capital N plus 1 and then plus 1 again. Oh, yeah. So capital N is 6, right? So I'll put that in. This is equal to 2 over, and then 6 plus 2 factorial, which is 2 over 8 factorial, which is a very tiny number. All right. Calculator, we'll put in 2 over, this is from an earlier problem. What's 2 divided by 8 factorial? Right, remember, 8 factorial is a very large number. It's like 40,320, I believe. I think I had that written up earlier. And rounding this to 6 decimal places, they said 0.0000496, so 0.00050. The error will be off by no more than 0.0000050 when I round that to 6, that 2 over 8 factorial to 6 decimal places. So adding up the first 6 terms of this series will give us a very, very close approximation, right? You'll be within 500 thousandths of the actual sum, right? Of what the sum converges to. Again, they run through that here. Great. Okay, moving on. So this is the other one. We did a problem like this before. So again, it's still bringing back that after adding up the first, capital N terms, the absolute value of the remainder must be less than just the absolute value of the next term of the series. So we're asked to find that capital N, right? Determine the number of terms necessary to approximate the sum of this series to within an error less than, 1,000th again. So very similar to a problem we saw earlier. So we gotta write this up. So here's this alternating series. Now they told us it's convergent. We don't have to check that, but you could do the absolute alternating series test and see that this is convergent. From 1 to infinity, 13, over 4n factorial, and then times, then you got your power of -1, -1 to the nth. This would cause it to alternate. Yeah, so the b sub n here, the terms that are being alternated in this series look like this, 13 over 4n factorial, which would definitely be, positive terms that are decreasing and going to 0, right? So this is convergent by that alternating series test, right? It satisfies all those conditions. So we're looking for a capital N here, right? How many terms would I need to add up? Again, less than, I'll just use less than again, less than b sub capital N plus 1. The absolute error after the adding up the first n terms will be less than just the next term of the sum, right? B sub n plus 1. Now b sub capital N plus 1 looks like this, 13 over, and then down here 4 times, and then replacing little n with capital N plus 1. And then you got factorial, right? So that's 13 over 4n plus 4 factorial. And they would like us to find a capital N so that this is less than 1,000, 0.001. So like before, I'm going to multiply by 1,000, multiply by this, we have 13,000 must be less than this 4n plus 4 factorial. And we saw in earlier examples, 7 factorial is 5,040, which isn't bigger than 13,000, but 8 factorial was 40,320, which is bigger than that. So again, like in previous examples, this 4n plus 4 has to be at least 8. Again, 8 factorial is greater than 13, the first factorial that's greater than 13,000. And then subtract, so n has to be greater than or equal to 1. right? Subtract 4, divide by 4, and that's a nice whole number. So this is telling me that, S1 gives the desired accuracy. I would only need to add one term to have an estimate that's within 1,000th of the actual sum of the series. So at least one term needs to be added here. Right? And then follow through and read the answer explanations. I think that's it. Yeah. So that's it for this preview version of this assignment. Now, as I said at the top of the video, questions I saw here may not be the exact same questions that you see when you work on the assignment yourself. But the objectives are all the same, right? The problems are hopefully similar enough so that watching me do them here help you out when you work on the assignment yourself. And some important things to take away from this video. I defined an alternating series. I know what that means. What does it mean for a series? What does an alternating series look like? We talked about the alternating series test. Right? When you have an alternating series, what are some conditions that should be met to be able to state that the series converges? Remember the terms that are alternating, right, need to be you're alternating positive terms, so positive, the positive positive, the opposite of a positive, the b sub n's, right? Those things that are alternating need to be positive and decreasing, right? Every term needs to be smaller than the previous one, and they need to be decreasing to zero, going to zero as n goes to infinity. Then you'll have a convergent alternating series. Then we had the definition of absolute convergence, right? If you have a series and you make all the terms positive or non-negative, and that series converges, then the original series is called absolutely convergent, and it would also be convergent itself, right? Remember, absolutely convergent series are also convergent themselves. Now, if you make all the terms positive, and you get a divergent series, well, then the original series is not absolutely convergent. All right, and then you go back and check, look at the original series. Now, if the original series diverges, it's just, divergent straight up. But if the original series converges and it wasn't absolutely convergent, then they would say that the series was conditionally convergent. Right? Lots of stuff to take away from here. A lot of definitions, lots of things to look at in this section. And I hope you understand it all and practice some more from the textbook exercises. And thank you very much for watching.